We finished off section 12.1 by talking about zeros of a function and how we can use synthetic division to find zeros of the function. We're going to continue that a little bit here in 12.2 when we're talking about zeros of polynomial functions. But we're going to start by talking about the factor theorem. And this has a very similar to feel to what we did in the first section. And that states that the polynomial x of k is a factor of the polynomial f of x if and only if f of x equals 0. Again, that should seem familiar because this is how we found if it was a root or a 0 or solution, is if this k right here, when we plugged it into the function, it equaled 0. So it's the same sort of process to see if it is indeed factorable. So in this case, x would be 5. And so I would take I would take 5, and I would take the coefficients of the function f, just like we did in the last section. I'm going to use synthetic division. And what's going to happen, you'll find out in just a second, that the remainder ends up being 0. So what this is telling us is that f of x is divisible by the binomial x minus 5. This right here becomes x squared minus 2x plus 3. And because of the theorem, what this would show is that if I take x minus 5 and now multiply it by this new polynomial that I got, so if I distributed this, I'll do the same thing with the 5. That these multiply together to give you the original. So using synthetic division is really a way to see what the factors are and to help us factor higher number polynomials or higher degree polynomials. And this will actually help us to solve these really complex higher degree polynomials. And we'll see that in just a little while. So go ahead and pause the video and see if number 2 is indeed factorable. So if you take a look at number 2, you'll find out the remainder is 3. Therefore, x plus 1 is not going to factor that polynomial for us. Number 3 is going to be one of those examples of why synthetic division is a nice way to factor higher degree polynomials. They actually tell us that -7 is a 0 of the function. So what you're going to do is you're going to use synthetic division and break down this polynomial. So go ahead and pause the video. I'll give you a minute to break this one down to find the 0. So what we end up getting is 8x squared plus 14x minus 15. Now, one thing I just want to point out, when they actually tell you -7 is a 0, you should get a 0. If you're getting anything else, that means you're making an arithmetic mistake somewhere in the process. So just kind of be aware of that. We're not going to give you any false hope anywhere by telling you that. So what this means now is that this function right here can be broken up as x plus 7 times the quantity 8x squared plus 14x minus 15. Now, what we can do with this binomial is already broken down as much as it is, or it can go, but this trinomial right here, we can still work with that and try to break it down. So what I'm going to do is I'm going to multiply by a times c. So we're going to get 120, and the factor pairs of 120 that add to 14 are 6 and 20. So we'll split it down the middle. 8x squared plus 6x, sorry, minus 6x plus 20x minus 15. And I'll split it and I'll get 2x times the quantity 4x plus 3x, or times 3. And then I'll take out a 5 here. So we'll get quantity, or 5 times quantity 4x plus 3. I apologize. This should be a minus 3 and this should be a minus 3. I'm going to regroup. This is going to be 2x plus 5 times the quantity 4x minus 3. And then we'll drop this down. X plus 7. Now, again, what this is saying is that the original function up there can actually be rewritten as 3 binomials. This is helpful in a few different ways. This is helpful because this will help us to find the zeros of the function, and the zero of the functions can help us, one, find the solutions, so what the zeros are, and those zeros will also help us graph those, and we'll come to that in a few sections as well. In this problem, we were lucky enough for the problem to state that -7 was actually a 0. In reality, there's infinite possibilities to guess what the 0 would be. And this is where the rational zero theorem comes in. And what the rational zero theorem does is it narrows down the possibilities. So you don't have to randomly guess what the 0 of the function is. It's not a perfect system where it gives you the exact number all the time, but at least reduces it from an infinite possibility to a limited list. And how you create this limited list is by doing this, where you're doing the ratio of P over Q. And P is the factor of the constant term, A sub 0, and Q is the factor of the leading coefficient. So again, it's really coming from the last number and the first number. And what we do is using those ratios, again, it lets us test different possibilities. In question number 4, it's given us a polynomial function, and it's asking us two things. It's first asking us to list all the possible rational zeros, and then to find all rational zeros and factor the function. So what happens is this right here is our P, and this right here is our Q. And we're going to start off by A and listing all those possibilities. This does get very tedious, especially depending on how big those numbers are. But again, it's better than not knowing where to start at all and guessing random numbers. So our number is 2. So what that means is that I have to find all the factors of 2. My factors are 1 and they are 2. And it's plus or minus because it could be different combinations to get the positive 2 in the end. Q is 6, and it has possibilities of 1, 2, 3, and 6. And remember, what's happening is you actually want the ratio of this. You want P over Q. So you're doing a combination. And you want to do this very systematically to make sure you're not missing any of them. So I'm going to start with the first P, and I'm going to do 1 over 1. And then I'll go to the next one. I'll do 1 over 2. And then I'll do 1 over 3. And then finally 1 over 6. Then I'm going to take the 2. I'm going to repeat that process. I have 2 over 1, 2 over 2, 2 over 3, and finally 2 over 6. Now, what you will notice is some of these repeat. 2 over 2 is a duplicate of 1 over 1, so I don't need to relist that. And 2, 6 reduces down to 1/3, which is a repeat, so I can get rid of that. In total, you have all these possibilities that would be a zero of the function. Now remember, each one of these is actually two numbers, a positive and a negative. So it's positive 1, negative 1, positive 1/2, negative 1/2. So there are actually 12 possibilities here. So what you're going to do is you just have to start going down the line. I'm going to start by testing 1 using synthetic division. Now, luckily it's synthetic division and not long division, so it does help kind of speed up the process. And you just have to test all the numbers. Sometimes you will get lucky and it will work out, and others you won't. I apologize. I actually have a typo right here. So I apologize. I think I typed the wrong numbers when I was setting this up. Yours on your worksheet should be correct. But let's fix the numbers here. So this should be 6, 7, negative 12, negative 3, and 2. And so what you end up getting is 13. And that should be 13, 1, 1, negative 2, negative 2, and 0. And this worked out well that we found one of the zeros right away. This is my constant. This is my first degree, so 1x. This is then 13x squared, and then this is 6x cubed. So we can say that this is x minus 1, because remember it's the opposite, times this 4-term polynomial. Now, unfortunately, this doesn't help us really because we can factor 3-term polynomials, but we don't know how to do 4 terms besides this method. So what ends up happening is you have to repeat this process again. So you're going to take this one, and we're going to redo that process. And we have 6, 13, 1, and negative 2. So I'm going to do the same thing, except now with this polynomial. So the idea is that you're knocking down the degree. So I started with a degree of 4, going down to a degree of 3, and then all the way down to a degree of 2. All right, so let's try now negative 1. Drop this down, I get 6. Negative 6, so that's 7. Then negative 7, and then this will be 6. And unfortunately, that's not a 0. So I've done plus 1 and minus 1. And actually, we should check to see if positive 1 is also a root, because you can have double roots. But I'm going to tell you right now it's not. So we're going to go to the next one, and we're going to do half. And I'm still using the 6, 13, 1, and negative 2. And I'm doing half. So 6 times half is 3. That'll give you 16. 16 times half is 8. That'll give you 9. And then I'll get 4.5, and that will be 2.5. So that is also not a root. So then we do negative half. And again, I'm using those numbers 6, 13, 1, negative 2. I'm going to get 6, and then this is negative 3. So then that's 10. And then you get negative 5. This will be negative 4. This will be 2. And we found the other root. So now I have x minus 1, x plus 1/2, and then I have 6x squared plus 10x minus 4. I want to factor this right here. I can take out a 2, and I have 3x squared plus 5x minus 2. And this factors down into 3x minus 1, and x plus 2. This 2 right here, I can kind of keep out. Otherwise, I can use it to get rid of that fraction, and that can become 2x plus 1, a little bit nicer to work with. So I factor this down. And again, what we're going to get to the point of, we're going to be using these. So like x equals 1, x equals negative half, x equals 1/3, x equals negative 2. We're going to use those to help us graph and obviously then to solve.